the APSC 172 midterm session. And opening the Q&A. Here we go. Here we go. Everything is ready and open. Hey, Peter. So, I wrote a few things down before starting the session. So, here we go. My name is Antoine, as you probably know already. And my email is right here, antoine@prep101.com. It's also somewhere like here, all the way up, you know. I will be helping you to get ready for your APSC 172 midterm. I think I've met a lot of you during the 174 session, which was a lot of fun. A very, very quick summary, because again, I think we have met before. I'm a tenured professor, not at Queen's, but I'm a tenured professor. I teach math for a living. I've been with CourseCram for 18 years, and I don't know, 400 sessions, 450 sessions. I really don't know. It's a lot of sessions, and it's been a few years I'm at Queen's. I think, I don't know, maybe 8, 9. Again, it's been a long time. Queen's is possibly my favorite university out of all of those universities I teach at with CourseCram, because, you know, you guys are awesome at Queen's. You are fun, you are funny, you ask questions during the session, you do not have boring sessions. There's rarely a boring session at Queen's, and I really appreciate that. So, as you probably know, I teach through examples. There is a course booklet and there's solutions, and you could look at those, but I'm not using them for my session. I'm going to teach you all of these topics through examples that I'm going to pick from my brain or from past tests. We're going to look at the questions that get asked a lot of times, and we're going to learn how to solve all of them, one topic at a time. Tonight it's until 9. Tomorrow is also until 9. The video, this session is recorded, and the video is made available to you guys 24 hours after we end. So the video of today, I even wrote that here, so because that's the most common question I get asked. The video of today will be available tomorrow, and the video of tomorrow will be available after tomorrow. I'm also making my session notes available to you. Those will be available at 9 p.m. on Thursday. So once we're done with the 2 days of the session, I will post the notes on the course page. If you have any questions, if you have any comments, if you have anything that's unclear, if you have problems you would like me to solve for you, really, you ask, and I will do my very, very best to answer you. You probably know, and if you don't know, then as someone who knows, my sessions are 100% dynamic, so I adapt to you. If you have certain questions you need solved, some things are less clear than others, I adapt to you rather than you adapt to me. Again, as much as possible, because eventually I want to cover all of these topics. You are my first break. You're my first session after a break of 2 weeks. So it was a nice, relaxing break between test 1s and midterms and test 2s. So it's good to be back. I'm happy you're here, and let's begin. That's my 4-minute introduction. If I've missed anything, please feel free to ask. And yeah, that's about it. Again, one last thing. My booklets are not printed. I know that CourseCram prints some of the booklets for other sessions, mostly because I don't intend on using the booklets at all. These are like for you guys to use outside the session, right? So I don't intend on using the course booklet at all for this. I'm going to use my own notes and your past tests, especially at Queen's, right? Like especially at Queen's, because as you've seen, they give you the past 3 years of tests, and I've given you up to 2017. So you have possibly 6 years worth of tests or midterms, and you know that they're very similar. You know that some questions repeat. So if we have a winning formula, why change it, right? So we're just going to focus on what comes on tests, on those topics, on those types of problems. It's been a winning formula for years and years, so why mess up with something that's working? right? So here we go. I'm going to do a very short introduction into lines and planes, then partial derivatives, then I'll probably jump to tangent planes, because that's a very common topic, and we'll just, go through the entire list of topics that we have here. I expect to be somewhere around here for today. Again, approximately, and then we'll finish the rest tomorrow. Excellent. So, short introduction into lines and planes. I will make this short, really, because we needed 4 problems. There's not usually a question directly asking for that. Perfect. So that's the topic at hand. Short intro to lines and planes. Right, so how do we write the equation of a line in R3? Again, we're working in R3, we're working in 3D. How do we write the equation of a line in 3D? We say the equation is a point plus t times the direction. So always, the equations of a line in 3D is point. So let's say the point is x naught, y naught, and z naught. And then t times the direction. Let's say the direction is ABC, and voila, you have the equation of the line. Of course, those are an x, y, z, right? So those can be written into an x, y, z form. If you want to expand them, you can say that x is equal to at plus x0, y is equal to bt plus y0, and z is equal to ct plus z0, right? So this is the expanded form of it. Very quickly, let's take an example. So if you have a line that is parallel to the vector 1, 2, 3, and it goes through the point, let's say 7, 8, 9, to keep it really simple. So what are the parametric equations of the line that's parallel to this vector and going through this point? And notice how I write my vectors with square brackets, and I write my points with parentheses, just so you can see what's a vector and what's a point. You may not use the same notation. Whatever notation you use, that's fine. Whatever notation your teachers use, that's also fine. So this would be x, y, z is equal to 1, 2, 3, t plus 7, 8, 9. Or x is equal to t plus 7, y equals to 2t plus 8, and z is equal to 3t plus 9. Let me give you another quick example. Sometimes they like to ask this at Queens. For example, what would be the equation of the x-axis? So if our line was the x-axis, what would be the parametric equations of the x-axis? So the x-axis is parallel to the vector I, the unit vector I, which is 1, 0, 0. Right? The x-axis has the direction of 1, 0, 0. And the x-axis goes through the origin, which is 0, 0, 0. So the x-axis is parallel to this vector, and the x-axis goes through the origin, which is 0, 0, 0. So the equations of the x-axis would be x, y, z is equal to 1, 0, 0, t plus 0, 0, 0. Specifically, if you want to write it in terms of x, y, and z, x is equal to t, y is equal to 0, and z is equal to 0. Which, if you think about it for 2 seconds, makes sense. On the x-axis, we have x values and no y values or z values. On the x-axis, the points are x equals to 5, y equals 0, z is equal to 0. So on and so forth. Right? To get a point on the line, just as a side note, in case we ever need this. So let me just put a blue line here, as in like just saying we're working with lines. In terms of how do we get a point on the line? So to get a point on a line, just give t a value. So let's say this line, for example, if I pick this line. So if you have this line, then you can take t equals to 0, and that will give you the 0.789. You can take the point t equals to -1, and that would be 666. Oh, 666 cubed. We can take t equals to 1 on the line, and that would be 8, 10, and then 12, and so on. So for different values of t's, we get different values of the points on the line. Right, next topic at hand is planes. Again, I'm going to put a blue line to indicate that it's a topic. If you have any questions, please do ask. This is a short introduction to lines and planes if you came in late. So what's the idea behind, how do we find the equation of a plane? A plane is an infinite surface like this, like an infinite sheet of paper. To find the equation of a plane, we need a vector that is perpendicular to the plane, which we call the normal vector, n. By the way, if this is a normal vector to the plane, then this is also a normal vector to the plane, then this is also a normal vector to the plane, then this is a normal vector to the plane, right? There's nothing particular about the perpendicular to the plane. Any vector that's perpendicular to the plane, that serves as a normal. So we need to find the equation of a plane. We need n, which is a normal vector to the plane, which means a vector perpendicular to the plane. You know the symbol perpendicular. Really, any vector works. And we need a point P0 that's in the plane. And the parametric, sorry, not the parametric, the equation of the plane would be, let's say n was the vector a, b, c. And then the point in the plane would be x naught, y naught, and z naught. Then the equation of the plane would be a, x minus x naught, plus b, y minus y naught, plus z, z minus z naught is equal to 0. So it's rare that they're going to ask you a question directly on planes, and eventually they'll ask you a question about tangent planes, and for tangent planes we're going to use a slightly different method, so we're going to get to that right away. Just a couple of notes. First, an example. So let's say you want to find the equation of the plane that's perpendicular to the z-axis, and it goes through the point 1, 5, minus 2. So we have a plane that is perpendicular to the z-axis and going through the point 1, 5, minus 2. So to find the equation of said plane, let's say this is the plane. Right, it's perpendicular to the z-axis, so the z-axis is perpendicular to the plane like this. This is the z-axis. However, you want to make the z-axis. So what's a vector that's perpendicular to the plane? A vector that is perpendicular to the plane would be the vector 0, 0, 1, which is basically the vector that's making up the z-axis. So that's the vector that's perpendicular to the plane. That's the point to the plane. So the equation of the plane is 0, x minus 1, plus 0, y minus 5, plus 1, z plus 2 equals to 0, which is basically z equals to minus 2. A couple of notes about this before we go to partial derivatives and other issues. First of all, if you are given the equation of a plane, so if you're given x minus 2y plus 3z is equal to 8, so you can right away see a normal vector to the plane. So right away, you know that n is equal to 1 minus 2, 3, 1. -2 and 3. I can put the invisible one if you want. So you can see right away what's a normal vector to the plane. Also, if you want points on a plane, how do you find points on this plane? Let's say this is the plane. How do you find points on this plane? What you find x, y, z that satisfy this equation. So you find x, y, z that satisfy the equation of the plane. So for example, here I can make x equals to 8 and y and z 0. I can make x is equal to 4, y equals to -2, and z equals to 0, right? So any x, y, and z that would satisfy the equation of the plane, that would work. And finally, this is, so this would be one note. This would be another note. How do you find a line intersecting a plane? Because sometimes they ask you this. So how do we find what's the intersection of a line and a plane? I'm going to give you this right away as an example. So let's say our line is whatever, x, y, z is equal to 251 t plus -101, and let's say that the plane has equation 2x minus y plus 3z equals to 15. So how do you find the line intersecting the plane? By the way, if you don't know this symbol means intersection. Basically what you do is you plug the x, y, z of the line into the plane, and then you solve for t. So the equation of the line is x is equal to 2t minus 1, y is equal to 5t, and z is equal to t plus 1. You're going to take those and you're going to plug them into the equation of the plane. That'll give us 2 times 2t minus 1 minus 5t plus 3 times t plus 1 equals to 15. That is a simple equation. Sure, Jamie, give me a second. I will come back to this. So if you give me 2 seconds, I'll get back to your question. So if you're solving for this, this is 4t minus 2 minus 5t plus 3t plus 3 equals to 15. So 4 minus 5 is minus t, plus 3t is 2t, and minus 2 plus 3 is 1, so that's equal to 14, so t equals to 7. So you can replace that in here, and you get that the line intersecting the plane is the point where t equals to 7. So 14 minus 1, 5 times 7, and then 7 plus 1. And that, ladies and gentlemen, is how we find the intersection of a line and a plane. Now, to go back to the example before, to answer Jamie, the question says the plane is perpendicular to the z-axis, right? This comes from the question, right? So it's saying find the equation of the plane that's perpendicular to the z-axis and going through the point 1, 5, minus 2, right, Jamie? So if we're given that the plane is perpendicular to the z-axis, and the z-axis is just 0, 0, 1, right? I'm not sure if I understood your question or not. If not, please feel free to re-ask. By the way, how'd you guys do on the 174 test? How was the 174 test, since, you know, almost all of you should have been there? Was it okay? All right, here we go. Perfect. So positive things. Oh, they haven't finished marking yet. Wow, so cool. So once you know, let me know. Oh, God bless you too. So perfect. So let's make 172 even better than 174 if that's possible, and help you, you know, ace that test too. So that's my only introduction to lines and planes. I don't want to do more. I want to focus more on tangent planes, because that's the question that gets asked. So I'll even write this in blue. Tangent planes, right? Tangent planes, not just regular planes, have special formula. Of course, special is just a, you know. So for tangent planes, we're going to discuss special formulas or special forms, whatever. So that's not something that I'm looking at right now. Right now, I'm going to discuss with you the idea of a partial derivative. So the next topic at hand is partial derivatives, because I need those for the tangent planes. I need those for several stuff. And I'm going to try and keep the same idea that when I, you know, underline with blue, that means it's a new topic. So we'll see how much I can continue with this. So right now we're doing partial derivatives, higher derivatives, and then we'll see where that takes us. So to understand partial derivatives, you must know, and I'm not going to go through this because I'm certain you know this, that there are functions of multiple variables. So you've met this. So we have a function. So for example, we can have a function of two variables, a function of x and y, and that could be really just anything. So let's make it x squared y minus 3e to the y plus 4 ln x, whatever, something. So I can now ask, what is the derivative of this function with respect to y, or the derivative of this function with respect to x? Now, I need you to pay very close attention, because we're going to need this tomorrow when we do contour maps. Okay, so the understanding of finding this is, very simple. I agree. But I need you to understand the nuance of what I'm doing. So what is del f del x, right? So this is the partial derivative of f with respect to x, which we write it sometimes as f sub x. Okay. We all know that this is finding the derivative of f by keeping y a constant. So you derive the function with respect to x and you pretend that y is a constant. So this would be 2xy plus 4 over x. And then if I ask you, what is the partial derivative of f with respect to y, which is f sub y, and that would be the derivative of f with respect to y, meaning I pretend that x is a constant and I derive with respect to y. So this is x squared minus 3e to the y. That's the basic idea. Now I want to dig a little bit deeper. What am I saying here? Okay, what am I saying here? This is the rate of change of f with respect to x, meaning we keep y a constant. So we don't change y, we just change x. So this is, I'm going to say this in like more English rather than math. So the rate, sorry, sort of, okay, I'm going to say again, this is not entirely true. Okay, the rate of the change in f given the change in x, right? Again, it's not exactly that, but it's the change in f. So how f changes when x changes. So this is the change in x. So if y was kept at the same level and x moves 1 unit, so how does the function change? And that'll be very useful to us when we look at contour maps. So basically, I'm doing this tomorrow, but just to give you a sneak preview. So if we have a bunch of contour maps, we're going to say, okay, we're at this point. I'm going to make X change 1 unit. So let's say this is 1 unit in X. So if X changes 1 unit in X and Y remains constant, because I'm going only horizontally. So what's the change in the function? The function jumped 1, 2, 3 contour maps. So let's say that's a change of 6. For example, every contour map is 2. So we can say that f sub x is approximately 6 because it jumped 3 contour maps and every contour map is a jump of 2. Therefore, f sub x is 2. That's how we're going to approximate f sub x and f sub y on contour maps. Again, tomorrow, but this is a sneak preview. And this is also the same idea. This is the change in f as y changes. So x remains a constant. Right, so that is something that we're going to have to deal with tomorrow. When we have functions of multiple variables, we can have now mixed derivatives. So I can say, what is the second derivative with respect to x? So del 2f del x squared, which we can write it as fxx. So this is the derivative. This is the derivative with respect to x of the derivative with respect to x. Right, so I'm deriving with respect to xy, or with respect to x twice, or the derivative with respect to x of the derivative with respect to x. Right, I'm giving you several ways of writing this. And simply here, let's say that would be deriving this with respect to x, and that would be 2y minus 4 over x. And I can say, what is del 2f del y squared? Which is fyy, which is the derivative with respect to y of the derivative with respect to y, or the derivative with respect to y of f sub y. Again, I'm writing all the possibilities. So what would it be here? I'm deriving this with respect to y, and that would be minus e root of 1. I see no questions and no comments, so I assume everything's fine. Again, we have this unspoken agreement that if there's anything not going your way, you would tell me, right? This is Queens, so we have this secret thing going on where you tell me if there's something unclear and I fix it. And if you're not telling me, then I assume everything's fine, right? Okay, so now we can talk about mixed derivatives. So I can say, what is the derivative with respect to x of del x del y? So which one do I do first? Do I do x first or y first? So if I'm doing now a partial derivative with respect to x and with respect to y. So it's twice, a derivative twice, once with respect to x and once with respect to y. So which one do I do first, the x or the y? And the answer is? You do know? Okay, well, the answer is it doesn't matter. For all the functions that we will see in this course, for all the functions that you will encounter in this course, there's a theorem called Clairaut's theorem that says it doesn't really matter. So this could be the derivative with respect to x of f sub y, but also the derivative with respect to y of f sub x. This is what we call Clairaut's theorem, meaning the order doesn't matter. The English version of Clairaut's theorem is the order does not matter. Of course, this is not true for all functions. This is not true for all functions. This is for all 172 functions. So all the functions that you encounter in this course, the order of derivative does not matter. So you can take with x first or with y first, it doesn't really matter. And we can check that, right? So let's derive this with respect to x. We would get 2x. Or let's derive this with respect to y. We would get 2x. So the order of our derivative doesn't matter. Right? So the order of our derivative does not matter. And that could be really any derivative, right? You can just do f(x(x, y, y, z), like f(x(x, y, y, z). So twice with respect to x, twice with respect to y, and once with respect to z. So let me give you another example. This is an example I personally like. So if I told you that f(xy) is equal to x to the y, and I'll tell you why I like this example particularly. So what is del f del x? And what is del f del y? Can I give you 30 seconds to do that? And the derivative with respect to x, we consider y to be a constant. So this is x to the power constant. If it's x to the power constant, that means I'm deriving a polynomial. So the derivative is constant x to the constant minus 1. Now, if I'm deriving it with respect to y, then it's an exponential. See here, I'm going to say this is the polynomial rule. But if I'm finding the derivative with respect to y, that means this is now an exponential. X is considered a constant, so it's a constant to the power y. Tell me something, if you remember it. What's the derivative of a constant to the power x? This is from 171. So what would be the derivative of b to the power x? That would be b to the power x times ln b. Right? If this wasn't an e, the derivative of e to the x is e to the x, but the derivative of 2 to the x is 2 to the x times ln 2. So the derivative of b to the x is b to the x ln b. So here, what's the derivative of x to the y? X is considered a constant, it's x to the y times the ln of the base, so times ln x. And this is because it's a general exponential rule. And I like this because it's fundamentally different. The derivative with respect to x is fundamentally different from the derivative with respect to y. One of them is a polynomial, the other one is an exponential. Is this clear? So I'm not hearing any comments or questions or anything. So let's talk about implicit differentiation. So once I finish implicit differentiation, we can talk about linearization or linear approximation, and that would be the perfect introduction to tangent lines. So let us discuss the idea of implicit differentiation. So this is a new topic called implicit differentiation. And as of this topic, we're advanced enough to start looking at past tests and get questions from past tests to talk about this. So let me give you, actually, let's just go here and check 2021 very quickly. Yeah, you see 2021 has this. This is, we could use this from 2021. We could use this. There's no specific question about implicit differentiation, but I'm going to use this. No, I can't use this. I'm going to use this. So given this, I'll keep it very simple. So given this, find del z del x. And I'm going to show you two ways of doing this. I don't think you've done both ways in class, but if you haven't done the second way, then that's fine. We can just skip. So let's look at this. And this is very, very much APSC 171. So this is not a very difficult topic. So just by saying this, find del z del x, what do we assume? Just by telling us, here's an equation, find me del z del x, what do we assume? What is implied in this question? What's implied in this question is, somebody will say it, partial derivatives, yes. Y is a constant, not for now, yes, AA. What's implied here is that Z is a function of X and Y. Right? Because I'm saying I'm finding the rate of change of Z with respect to X. So I'm assuming that Z is a function of X and Y. And then by finding the partial derivative of Z with respect to X, I'm assuming that Y would be a constant. So this implies the idea that they said, find zxy, it tells me that Z is a function of X and Y. Sometimes they'll add this. So they'll say, given this, sometimes they'll say it, not all the time. They'll say, defines Z as a function of X and Y. Like sometimes they say, let me just be clear, sometimes they add this sentence, that this equation defines that as a function of X and Y. Or they'll say, this defines Z is equal to fxy. So Z as a function of X and Y. So what does that mean? It means that when I'm finding del Z del X, this is going to be kind of Z prime, right? This is going to be Z sub X. It's going to be the derivative of Z with respect to X, which is not one or something, like it's a derivative. Z is a function of X and Y. So Z has a derivative with respect to X and Z has a derivative with respect to Y. So how do I do this? I simply derive the entire equation with respect to X. So I derive the entire equation with respect to X. Now, please remember, Z is a function of X. So what's the derivative here? Here, I have to use the product rule. See here, I have to use the product rule. So it's this times this. The Y, you can put it anywhere you want because it's a constant. So the derivative of xy is y times z plus xy times the derivative of z with respect to x. Do you follow what just happened? I'm going to make it even more clear. I'll go even slower. So this is the derivative of xy with respect to x times z plus xy times the derivative of z with respect to x. Is that better? I'll even make it more clear by saying for this, I use the product rule. Now, the derivative of 2x is 2. The derivative of 2y is 0. and the derivative of z with respect to x is del z del x. And now we just isolate or solve for del z del x. That's basically implicit differentiation. So the derivative of xy with respect to x is y, yz plus xy del z del x is equal to 2 plus del z del x. So xy del z del x minus, excuse me, del z del x is 2 minus yz. So I factor out del z del x, that'll leave me xy minus 1 equals to 2 minus yz, and therefore del z del x is equal to 2 minus yz all divided by xy minus 1. Okay, let's pretend that you did not get this fully and ask you another question. Here's another example. So in 2016, this is what they asked. By the way, older tests are relevant because I'm going to leave this up to you. I'm not going to do this exercise right now. But I mean, look at past tests and look at current tests. Sometimes some questions are recycled. Sometimes they'll just bring back a question from 2017 or 2018 or 2016. Like a lot of the times, you know, something will just come back. So it's important to do all of those tests. So in 2016, they told us e to the xz equals to xy plus z squared defines z as z is equal to fxy, comma, find, or semicolon, find del z del x and del z del y. So how about I give you 30 seconds to try and work at least one of those two. By the way, yes, there is a break. The break is in about 100 minutes. Like the session is 3 hours and a half. So I don't remember how I scheduled the breaks, but we're gonna do about like an hour, then 15 minutes, then an hour, then 15 minutes, then an hour, something like this. So it's not exactly this because, you know, we might change things a little bit around, but something like this. And I say this because some people want to order food and some people want to take a, you know, washroom break or something. And so let's say you want to find del z del x. So what you're going to do is we're going to derive with respect to x this entire equation. So what is the derivative with respect to x of this entire of this? We're going to derive, sorry, with respect to x this entire equation. So what's the derivative of e to the xz? I remind you that this is a function, and this is a function of x, and this is also a function of x. So the derivative here is e to the xz times the derivative with respect to x of xz, right? Chain rule. Equals. The derivative of this with respect to x is just y. The derivative of this with respect to x, chain rule, that would be 2z times the derivative of z with respect to x. Let me write this here. Do not forget chain rule, which I'm sure you won't, but just as an extra precaution. So here, this is a product. So e to the xz times the derivative of the first times the second plus the first times the derivative of the second equals y plus 2z del z del x. And now I proceed basic algebra to solve for del z del x. So I multiply this out. So z e to the xz plus x e to the xz del z del x is equal to this. So I move this here and I move this there. So x e to the xz del z del x minus 2z del z del x is equal to y minus x e to the xz. I factor out del z del x. That leaves me with x e to the xz minus 2z is equal to y minus x e to the xz. And I solve for del z del x, which is y minus x e to the xz. And this is x e to the xz minus 2z. It's a lot of algebra, but really this is what this is. Let's take now, so this was part one of the problem. Let me find the derivative del z del y. So if I derive with respect to y, what do I get? Again, I'm going to give you 30 seconds. So let me give this a title. So now, for finding del z del y, I'm going to derive this with respect to y. Please take 30 seconds to find it. So this is a function of y, this is a function of y, and this is a function of y, but we don't have a product rule here. So the derivative of e to the xz is e to the xz times the derivative with respect to y of xz. Basically, x is a constant, so it's x times del z del y. The derivative of this with respect to y is x. The derivative of this with respect to y is 2z times del z del y. So I can move del z del y here and factor it out. So del z del y times x e to the xz minus 2z is equal to x. So del z del y is equal to x over x e to the xz minus 2z. Now, we may need this for other topics, but that's the idea behind implicit differentiation. Why is it e to the xz times x? So we're talking about this line, A. Okay, so you're taking the derivative, I'll do it in here. You're taking the derivative with respect to y of e to the xz, which is e to the xz times the derivative with respect to y of xz, right? Chain rule. Now remember, x is a constant. So the x comes out. So e to the xz, and then the derivative of xz, again, x is a constant. So this is x times the derivative of z with respect to y. And that's what we got here. Thank you for asking. Do we have any other questions? Right, so that's, ladies and gentlemen, implicit differentiation. Sure. The algebra for the first one. So you mean after this step here? So after we did the chain rule and then the product rule here, this is the product rule here. I'll say product rule. Remember, our goal is to isolate del z del x. We want to solve for del z del x. So as a first step, I'm going to multiply this through to get this. So now the del z del x is kind of free. So you move everything with del z del x to this side and everything without a del z del x to the other side. So everything with del z goes with del z del x goes to the left, and everything without del z del x goes to the right. You end up with this. You factor out del z del x, so this gets factored here. You're left with x e to the xz minus 2z, which is right here. And then you divide by it here, and you get del z del x. What happened to the z e to the oh, sorry, yes, sorry, that's my mistake. That's a z. Right, when I moved it to the other side, I made it to next. Sorry, you're right, this is a z. Thank you for catching that. So when I moved the z to the other side, I copied it wrong. And the product rule seems to be bothering people here. Look, I want to find the derivative with respect to x of xz. Let's just do this on the side. What is the derivative with respect to x of xz? I remind you that x is obviously a function of x, and then z is a function of x, correct? Z is a function of x. So I'm going to take the derivative with respect to x of x times z plus x times the derivative with respect to x of z. Now the derivative of x with respect to x is 1, so that's 1z, and that's just the derivative of z with respect to x. That's how I got the product rule right here. Does that answer your question? Now, I didn't need to do it in the second example because look, there seems to be something off with my connection. Give me a second. Sorry. Yeah, I think there's a loose cable. Oh, hold on. There's a disaster is happening. Well, 1 second. And now the camera is off. Just give me 2 seconds, guys. Let's see what's happening with the file.
We can see everything. Like we can still see the screen and you, just so you know. You look frozen from
yeah, it's not. You
okay.
Can't see me. I've moved a couple of things.
Okay.
Sorry, just give me 1 second. I'm gonna restart this. Somehow today, it's bizarre. We won't lose the connection. We'll just lose the feed for 2 seconds. There's a loose cable somewhere.
Yep. So right now we're just seeing the restart.
Do you have any other questions, ladies and gentlemen, boys and girls? Excellent. Next topic at hand is linear approximation. So I don't remember, do you call it linearization or do you call it linear approximation? I forget. Basically, this is LXY. Perfect. Just give me 2 seconds. Oh, thank you. Sorry, I just needed to let head office. No, perfect. So, what's the idea behind the linear approximation? Let's dig a little bit into the theory. What's happening here? So you have a surface, you have a complicated surface. Let's say like a, mountains and whatever, like a weird surface. But you're interested in that surface only near a certain point. So let's say your surface is, I don't know, something like this, whatever, this is a surface, right? Whatever the surface looks like. And you're only interested in that surface near a certain point AB. So let's say this is the function fxy, which is a surface, right? fxyz is equal to fxy is a surface. I'm going to talk a little bit more about this once I finish talking about linear approximation. And you're only interested in this surface, near this point, which is the point AB. So this is the point AB. So what do? How do we approximate this function, but only near the point AB? We create what's called LXY. And LXY, ladies and gentlemen, let's do it in purple, is like a tangent plane right here. So what we create is, this is LXY. We create a small tangent plane around LXY. Now, of course, if this was LXYZ, then it's not something that we could see. We're in the 4th dimension and we can't really see it, but it's still called like a hyperplane, a plane of some sort. So this is going to be an approximation of fxy for any point near AB. So the idea is that LXY or fxy, the complicated surface, will be approximately the same thing as LXY for all the xy's, for all the points that are near the point AB. And think about it. Let's say my hand is the surface and I'm interested in everything near like this point right here. So I just get, here we go. I just get this. So I get like a plane, and I just put the plane, I don't know how close I can get, on that point. So my surface is approximately the same as this purple paper for all the points around that point of interest to me. Right? You can see it. I don't know how good my camera is, so I can get closer or further. So the idea is that the surface fxy is approximately equal to the LXY, which we call the linearization or the linear approximation for all the points xy near AB. So in English, LXY approximates fxy near the point AB. Now, the formula for LXY is so easy and so useful at the same time. LXY is equal to f at the point AB plus f sub x at the point AB times x minus a plus f sub y at the point AB times y minus b. And of course, if we had a third variable, then that would be f sub z at ABC times z minus c. Great. Can you tell me what this is? What is this? So yes, it's the linear approximation, but realistically, making things a lot simpler, what is this? What is this? In reality, ladies and gentlemen, this is what? Exactly, AA. This is the equation of the tangent plane. So if you take Z and you put it equal to this, then this is the equation of the tangent plane at the point A, B, and F of A. Because a point has three things, X, Y, and Z. So this is X, this is Y, and this is Z. Z is F of AB. So this is one way of finding the equation of the tangent plane. So they can ask you this in a form of find the linear approximation, or they can ask you this as in the form of find the equation of the tangent plane at this point. So it could be a tangent plane question, or it could be a linear approximation question. So in 2020, they asked this. So this is an example from the midterm of 2020. Actually, let me just go get it from 2020. It might be easier. So 2020 questions. Here we go. So this is an actual question from 2020. Let g of xy be x to the 4 plus xy squared. Find an expression for the linearization Lxy at the base point 1, 2. So do you want to take 30 seconds and answer this for me? So Lxy is equal to, I'll go slowly writing the formula. It would be the function at the point 1, 2. The function, the derivative with respect to x at the point 1, 2 times x minus 1. Then the derivative with respect to y at the point 1, 2 times y minus 1. So let's find all of these quantities. What's g of 1, 2? This is 1 to the 4 plus 1 times 2 squared, which is 5. G sub x is equal to 4x to the power 3 plus y squared. So g sub x at the point 1, 2 is 4 times 1 cubed plus 2 squared, which is 8. G sub y is equal to 2xy. So g sub y at the point 1, 2 is 2 times 1 times 2, which is 4. And here you go. Shouldn't it be y minus 2? Yes, of course it is. So, thank you, John. So Lxy is equal to 5 plus 8 times x minus 1 plus 4 times y minus 2. And we don't expand Lxy, we leave Lxy as it. Why? Because then they could ask us a second question. Did they do this in 2020? they didn't do this in, oh, they did this in this question. So they did this in this question. So let's do this question from 2020 also. I'm just going to copy it to give you some time to read it. So this is also 2020. They asked them this question. By the way, in past years, mostly before COVID, after COVID, we had a couple of years where the tests were online. So the tests were hell and difficult and strange. But I mean, Queens was focusing on giving questions a lot like this, where you don't actually need to compute as much as you need to understand. Like they're giving you these values, right? They're not asking you to find them. Like here, we had to find them. Here, they're giving you these values. They just want you to use them. So hopefully the trend continues. Given a function like this, that we don't know what the function is, but we know the values that we need to work with this function. We want to find the linearization of h. So we want to find Lxy at the point 1 minus 2, and then we're going to use it to evaluate, to approximate this point. So maybe take 30 seconds to write this down. It shouldn't take us more than a minute to be able to do this. By the way, I'm interested in your opinion about something when you have a second. I was asked by CourseCram if we go back to sessions in person or online. So I'm just curious about what you think. I'm asking about your opinion. If you could maybe take 2 seconds to just. Last time I did this, it was literally 50-50. I don't think it would be recorded if it's in person. In person, it means you have to be there. Because slowly, the sessions are going back to in person. Not everywhere, but I'm curious of what you think. I don't know how much of this is true, but I'm also understanding that students are getting together and they're all watching at the same time, and not just every person is registering and stuff. And that's, not the whole reason why we're going back in person, but part of the reason. But anyway, I'm curious what you guys think. Notes will always be uploaded. Notes will, no matter where we are, the notes will be uploaded. But if the session is in person, then what are we gonna record? There's nothing to record. There will be only notes. So here we go. It seems, most of you want this to stay online. Cool. I don't know how, I don't have the power of decision over this, but if CourseCram asks me to go back in person, I'll just go back in person. I don't know if it's going to happen or not, but it may actually happen for the final exam, or maybe part of the session. Maybe parts of the session will be online and parts will be in person. I'm not really sure. So I'm just curious what you thought about this. It's strange because last time I asked in a Queen's session, it was literally 50-50. Anyway, so let's go back to this. Lxy is equal to, we have everything we need. It's going to be a g or h of 1 minus 2 plus h sub x at 1 minus 2 times x minus 1 plus h sub y at 1 minus 2 times y minus 2, which is y plus 2. So Lxy would be equal to 4 plus 3 times x minus 1 minus 2 times y plus 2. And we do not expand Lxy. We just leave Lxy the way it is. So why do we not expand it? Because we need it here. So we're going to say, what is h of 1.03 minus 1.98? So what is the function? it's approximately equal to L of 1.03 minus 1.98. As we said, L approximates the function. The linearization L approximates the function. It's so much easier to plug things into H. Look, it's 1.03 minus 1, and it's minus 1.98 plus 2. You see how when you don't expand it, it's very simple. So this is 0.09, and this is 0.02 times 2, 0.04, and this is 4.05. Very simple, very straightforward. So I want to say a few words about differentials, but I think we should take a break so it doesn't go too far in the session, and then it's not worth it taking a second break. Do you have any questions about LXY? Any questions at all? After this, I'm gonna discuss briefly the idea of differentials and how they link to linearizations, and then after that, I'm gonna do the famous topic of tangent planes. And when I do tangent planes, we're gonna do the super famous gradient, and then when we do the gradient, then there's a whole lot of things that we can do. We're gonna do some harder problems. Just before we go on break, just like a quick topic check, we did implicit differentiation, we did linearizations. I'm gonna do differentials after the break, and then we're gonna do tangent planes. Fair enough? I think now is a great time for a break. It is 6:43. Let's be back in 15 minutes, 6:58. All right, see you guys in just a bit. So we are back. Let's continue. So the idea of differentials. Differentials measure change. Let me go through this with you. I don't know how much of this you've covered this term. You will probably let me know. So if we have, let's say, a function of xy, so a function f of xy, so we are given this, let's say, what would be df, right? df, by the way, d something, is an approximation of delta f, which is the change in f. So since delta means change, so delta x would be the change in x. So for example, dx is an approximation of delta x, which is the change in x, and so on. We're not going to do it for every variable out there. So df is the change in f. And what's that? The formula for this, it's f sub x times dx. So the change of f when x varies times the change in f plus the change f sub y, so the rate of change of f with respect to y times the change in y. And of course, if we have three variables, then that's three variables, so on and so forth. Look, why is this exactly the linearization function? Why is this the same thing as the formula for Lxy? Look, Lxy, the formula is f of f sub x, I won't say of xy, times x minus, sorry, I forgot f of ab. So it's f of ab plus f sub x at ab times x minus a plus f sub y at ab times y minus b. Now, I want you to look at how these formulas are the same. So if you move this to the other side, we will get Lxy minus f of ab is equal to this. And what's the formula for differential? The change in f, the change in the function, is the change in, the rate of change of f with respect to x times the change in x plus f sub y times the change in y. And look, aren't those exactly the same? So Lxy minus fab is the change in f when the point goes from ab to xy. So we had the point ab, and then we're changing it to a point xy, right? So we're talking about a point xy near the point ab. So it's as if the point ab became the point xy. So this is the change in the function. This is the change in x, because x was a and it became x. And then this is the change in y. So y was b, and then it became a new y. So you can see that those are exactly the same function. This is exactly the same idea. So technically, the function at xy is approximately equal to the function at ab plus the change in f. And this again comes from this, because fxy is approximately equal to Lxy. See, fxy is approximately, we know that fxy is approximately Lxy. And we know that Lxy is fab, I'm gonna write it again, plus all this. And that's basically your idea. So if they ask us a differential question, I don't know if there are any differential questions in the tests. I haven't seen any. I don't know if you even covered it, but I decided to cover it, so we cover absolutely all the topics. So let me just give you a quick example. Nothing is complete without an example. So let's say I have f of xy is equal to whatever, let's pick a function, x to the 4 plus xy squared. The same thing as before. And let's say that we're told that when we need to find df, the change in f, given that we go from the point 1, 2 to the point 1.1, 1.1, 1.9. So this would be your AB. This would be your, so that means your delta dx would be 0.1 and your dy would be minus 0.1. Sorry, this is my wife. She's telling me she's a bit late. Okay. So, what's df? First of all, let's find f sub x. F sub x is 4x cubed plus y squared. So f sub x at the point 1, 2 is equal to 4 plus 4, which is 8. F sub y is equal to 2xy. So f sub y at the point 1, 2 is equal to 4. So what is the change in f? The change in f is 8 times the change in x plus 4 times the change in y. So this is 8 times 0.1 plus 4 times minus 0.1. So the change in f is 0.4. Okay. Does that make sense in terms of linearization? Right? What is Lxy? Let's find Lxy. Lxy is equal to f of 1, 2 plus, and f of 1, 2, let's just find it here. F of 1, 2 is equal to 1 plus 4 is 5. So I'll do it right away. Lxy is 5 plus 8 times x minus 1 plus 4 times y minus 2. So if I were to find f at 1.1, 1.9, that would be approximately equal to L of 1.1, 1.9, which would be 5 plus 8 times 0.1 plus 4 times minus 0.1, which would be 5.4. I will say that in a second. Now look at this. What is this? What is this? This is basically f at 1, 2 plus the change in f. This is 5 plus the change in f, which is 0.4. And dx is when x goes from 1 to 1.1, dx is 0.1. And when y goes from 2 to 1.9, dy is minus 0.1. Right, when you go from 2 to 1.9, your dy is minus 0.1. The change in y is minus 0.1. No problem here. Do you guys see this? This is what I'm saying, AA. There is not really a point for it. It's just the same thing as linearization. But some books and some teachers, teach this formula of df is equal to like this. So I'm teaching it to you, so you have the whole picture, the entire thing, everything. So nothing that they can throw at you don't know. And that covers, ladies and gentlemen, differentials. So right now I would want to discuss with you tangent planes, and then once we do tangent planes, we're going to do some nice problems. We're going to look at past tests. There's going to be plenty of stuff to do with tangent planes. So here's the next topic at hand, tangent planes. So here's the idea. Surfaces can be defined in two ways. So please pay attention. I'm going to give you sort of a little bit more theory than what I did in other topics. Surfaces can be defined in two ways. What are the two ways that we can define surfaces? So a surface can be defined one way as z is equal to fxy. So we have a surface z is equal to fxy. Its graph in R3 is a surface. So the graph is in R3, and that makes it a surface. So how do we find the tangent plane to the surface? So how do we find the tangent plane in this case? So the tangent plane at the point x0, y0, and f of x0, y0, because always a tangent plane would have an x, a y, and a z. The x and y are x0 and y0, and the z, we find it by plugging into the function. So how do we find the tangent plane? Well, we know this. Lxy is equal to. We talked about this. The tangent plane is nothing but the linearization. So this is f of x0, y0 plus f sub x at x0, y0 times x minus x0 plus f sub y times, at x0, y0 times y minus y0. And we don't usually call it Lxy. What we usually call it is z is equal to. But we know that z is the same thing as Lxy. That part we covered, right? And f of x0, y0, that is the same thing as z0, right? So this is the point z0. I want to make sure that this is okay before I explain to you the next type of surfaces and the next type of finding tangent planes. Is this okay? I'm hearing no complaints. So what is another type of surface? Pay attention. The other type of surface is what we call a level surface. So what's a level surface? A level surface is when you have a function f of x, y, z equal to a constant k. That's what we call, ladies and gentlemen, a level surface. Level surface, meaning it's the surface where the function is equal to a constant. It's a level surface. What you know is level curves. Level curves are something that you are absolutely familiar with. Those are contour maps. Like, you do this, and you say this is 10, this is 20, this is 30, this is 40, this is 50. What are these? These are the level curves, meaning those are when f of xy is equal to constant. And the constant here is 10, the constant here is 20. So you are used to level curves. Now I'm talking about level surfaces. Let me explain to you this in a different way on the side. So this is a side explanation. Look. If we have a function z is equal to fxy, its graph is in R3. We talked about this. This is a surface. Okay. What happens when I set it equal to a constant? Sorry, I'm very OCD about my straight lines. They need to be stripped. So what happens when I set it equal to a constant? So what happens when I say fxy is equal to a constant? When we set a function equals to a constant, we theoretically lose a dimension. So we lose a dimension, meaning this becomes in R2, and in R2, that makes it a curve. So this, ladies and gentlemen, is what we call a level curve. So what's a level curve? It's when a function fxy is set equals to a constant. So fxy is a graph, and when you set it equals to a constant, it basically means you're cutting it through a plane and you're looking at the intersection of your surface with that one plane where z is equal, and that plane is z is equal to a constant. So it's basically taking slices of your curve. Imagine you have like a curve, like a hill like this, and you're slicing it with z is equal to 1, z is equal to 2, z is equal to 3, z is equal to 4, and you're looking at the imprint of that intersection with that z is equal to a constant. This is why when we get level curves, we get them sort of like this. So this is the level 10, where z is equal to 10. This is the level 20, where z is equal to 10. This is the level 30. This is the level 40, and so on. So along this curve, the value of z is always 40. Along this curve, the value of z is 30. This is why they're called level curves. A curve where the function is level, where the function is a constant. And we're going to deal with contour maps and level curves tomorrow. Right now, I'm interested more in level surfaces. So if I have W is equal to f of x, y, z, then its graph is theoretically in R4. Because f of x is in R2, f of xy is in R3, f of xyz is in R4. So the graph is in R4. So it's like some kind of hypersurface. When you set it equal to a constant, when you take f of xyz equals to a constant, you lose a dimension. So this becomes in R3. Therefore, this becomes a surface. And this, ladies and gentlemen, what we call a level surface. So this is the other type of surfaces that we have. We have a surface that's just a regular z is equal to fxy, which we saw it here. And we have a surface when we have f of xyz is equal to a constant. Sorry, I keep erasing things. And this is the other type of surfaces that we have, which is a level surface. Now, to be able to talk about planes to level surfaces, I need to introduce you to a very important notion, the notion of the gradient. And the notion of the gradient is very important because it's going to be used in more than one context. Okay? It's very important, yet it's very simple. What's the gradient? So what do we call, if I have an fxy, then what is the gradient of f? This is called nabla f. This letter in Greek is nabla, but just call it gradient f. And if I have a function f, x, y, z, then what is the gradient of f in that case? Right? It's very simple. The gradient is the collection of first derivatives. So here, it's the derivative with respect to x, the derivative with respect to y. What is this? This is the derivative with respect to x, the derivative of respect to y, and the derivative with respect to z. Okay, why do we care about the gradient? And this is the very, very important. I'm even writing it in, I'm going to write it in pink. Pink is reserved for the most important thing. The gradient vector. So the gradient vector, and this is very, 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 very important, is always, so there is no exception here. There's no like what if, is always perpendicular to the level, whatever you want. So curve or surface. Curve or surface. This is very, 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 very important. So if we have a level curve, not any curve, please, keyword level, right? Not any curve, it has to be a level curve. So if I have a level curve, fxy is equal to a constant, then the gradient will always be perpendicular to the curve anywhere you take it. So here, here, this is not perpendicular, this is perpendicular. And if I have a level surface, so if this is a level surface, f of x, y, z is equal to k, please, it has to be a level curve or surface, not just any curve or surface. What's happening again? Come on. This is bizarre. I don't usually have an issue with this. Okay. I guess we'll wait till next session. I will fix it on the next break. So if I have a level surface, then at any point, you pick the point you want, the gradient is perpendicular to the surface. So the gradient would be perpendicular to the surface at this point. So at the gradient at P0 would be perpendicular to the surface at P0. Okay. How can we use that in terms of tangent plane? That means the gradient of f at the point P0. Look, if you think of here, if you're looking for the tangent plane at P0, if you're looking for the tangent plane at P0, so let's say this is P0, and let's say this is the tangent plane at P0, then the gradient of f at P0 is perpendicular to the tangent plane at P0, therefore the gradient is basically n. The gradient would be the normal vector. And I tried to do this almost like a class. So of course faster than a class, but like with all the steps of the theory presented to you. So the gradient is always perpendicular to the level surface. I'll zoom in. The gradient is perpendicular to the level surface. So if I'm looking at the tangent plane, so if I'm looking at the tangent plane at the point P0, so what could I use as a normal vector to that plane? I would use the gradient as the normal, and I have P0. So I have the gradient, which is the normal vector, and I have P0 as the point. I can write the equation of the tangent plane. Of course, it has to be a level surface. So it has to be a level surface. Let me explain that to you through an example. So here we go. Shall we bother looking if there's a nice one in 2021? Yeah, so this is exactly 2021. We did part of this question. So maybe we look at 2020. Did they ask that in 2020? I don't think they did. They asked this, which I'm going to come back to. Okay, so now I want to do a go back to notes. I want to do an example from scratch. I don't want to do half an example. Then we'll go to the test and I'll show you, because what we saw on tests are parts of questions. I want to do like a big question that involves everything from A to Z. So here's an example that looks like the tests. So let's say you are given z is equal to x squared plus 2xy. Let's say we want to find, the equation of the tangent plane at the point 1, 0, 1 in two ways. First way, using z is equal to fxy, so using linearization, and the second way using the gradient. Okay, please pay attention. First of all, what is, if I have z is equal to x squared plus 2xy, then what's my fxy? Okay, before I start, I want to include a couple of notes so we can understand what's happening. If you understand what's happening, then everything becomes easier. Okay, so I gave you z is equal to x squared plus 2xy. What's my fxy? So what is fxy? No, fxy is x squared plus 2xy, right? So this is what the function of x and y is. Make sense? Of course, you all saw this. Also, if I tell you that the point is 1, 0, 1, then what is this one? That one is z. So that the one is basically f of 1, 0. Right? So this is z, which is equal to f of 1, 0. So if I plugged 1, 0 in here, I'm supposed to get 1. Do we get this? Okay. How do I transform this into a level surface? So how do I get a level surface? How to transform any z is equal to fxy into a level surface. Well, the answer is just move everything to one side. It's very simple. Make it z minus fxy equals to 0. So now this becomes a function of x, y, z equals to a constant. Now the constant is 0. Great. Who cares? As long as it's a constant. Right? So in this instant right here, so here we can make z minus x squared minus 2xy is equal to 0. And that, ladies and gentlemen, that's the function txyz that I made it equals to a constant. So now this became a level surface. This is a level surface. Why is it a level surface? Because it's an equation, it's a function of x, y, and z equals to a constant. Let's say you had, let's say plus 1 here, AA. You can move this and make it equal to 1, but you can always make it equal to 0. You can always move everything and make it equal to 0. It doesn't matter what the constant is. See, this is a level surface. You don't care what the constant is, right? It's irrelevant. You can always make the constant 0. You can move everything to the left-hand side, leave nothing on the other side, and your right-hand side on your would always be 0, and that would always work, and you would have no issues whatsoever. Fair enough? So back to this problem. So method number 1, I have z is equal to x squared plus 2xy. So this is my fxy. And I want to find the equation of the tangent plane at 1, 0, 1. So this is my AB. So basically, what's f sub x? F sub x is 2x plus 2y. So f sub x at the point 1, 0, that's 2. What's f sub y? F sub y is 2x. F sub y at the point 1, 0 is also equal to 2. And we know that f at 1, 0, that's the value of z, which is 1. So the equation of the tangent plane, we're using the formula for Lxy. Z is equal to f of AB plus f sub x times x minus a plus f sub y times y minus b. So if you expand it, because this is the equation of a tangent line, you can expand it. 2x minus 2 plus 2y, basically 2x, or basically 2x plus 2y minus z is equal to 1. Method number 2. Now I want to make it a level surface. So now I'm going to say z minus x squared minus 2xy is equal to 0. So that is the function of x, y, z that I set equals to a constant. And the point at which I'm finding the tangent plane is 1, 0, 1. So now I have a level surface. I have a level surface, and I would like to find the equation of the tangent plane. So I start by finding the gradient at t, the gradient of t, which is t with respect to x, t with respect to y, and t with respect to z. This would be minus 2x, minus 2x minus 2y, minus 2x and 1. And yes, in this case, I expanded to show you that it's going to be the same answer, AA. I expanded to show you that it will be the same answer, so you don't have to expand. So the gradient of t at the point 1, 0, 1 is minus 2, 1. So this would be a normal vector. This would be the normal vector to tangent plane. The point is 1, 0, 1. So how do we find the equation of a plane in general? It's a x minus x0 plus b y minus y0 plus c z minus z0. So let's expand it. Minus 2x plus 2 minus 2y plus z minus 1 equals to 0. So if I move everything to the other side, I'm going to get 2x plus 2y minus z equals to 1, which is exactly the same thing. Now, do you need to know both methods? Absolutely. Because not only they could ask you to do it, this is t sub x, t sub y, this is txy, anonymous. This is txy. So I'm finding t with respect to x, t with respect to y, and t with respect to z. Do you get that? No problem. Okay, I want to do more examples of this. This is by far not enough. So let's say here. No, 2021 doesn't have it. 2020. Okay, here we go. No, here we go. Here's a question from 2020. You'll see that this is partly what we did before, but asked slightly different. Then I'm going to ask you some harder questions in this. I'm going to make this a little bit harder, but just in time. So we have a function gxy at the point 3 minus 2. It has a value 5. And it has a gradient gx gy, again, at the point 3 minus 2 to be equal to 4, 2. Find the equation of the tangent plane to the graph z is equal to gxy at the point 3 minus 2. Let me give you 30 seconds to think about this and get back to me. Well, there's really nothing there, right? So the equation of the tangent line in this case is the same thing as Lxy, which is g of 3 minus 2 plus g sub x at 3 minus 2 times x minus 3 plus g sub y at 3 minus 2 times y plus 2. So g of 3, 2, they told us is 5. G sub x, they told us is 4 times x minus 3. And then g sub y, they told us is 2, y plus 2. So very simple, very direct question if you understand what they're asking. Right? Let me ask you a question from here. I want to go to here. I want to go. Yeah, we're going to do some of those, not a problem. Nope, we're going to do this. See, some of those are harder questions. Here we go. Tangent planes. Those are very nice questions. But I wanted to do just a general question. There was no general question. Here we go. That's what I want. So this is a question from a past test that does exactly what I do. I don't know if this was 2017 or 2016 or something, but anyway, this is a past test. Let me give you 30 seconds to do this. By any method, find the equation of the tangent plane to this surface. So we do not have a choice here except to use the idea of a level surface. And AA, here it's the level surface is not equal to 0, it's equal to 4. So that's not a problem. So this is the fxy, or let's get used to calling it txyz, if you don't want to call it f. This is a level surface because it's a function of x, y, and z is equal to a constant. So the gradient of t, you want to take a moment and find me the gradient at t? So the derivative with respect to x, the derivative with respect to y, the derivative with respect to z, at the point 1, 2, 1, the gradient of t is going to be equal to, when x is 1, 1y is 2, and 1z is 1. This becomes the normal vector to the tangent plane at the point 1, 2, 1. Basically, this is perpendicular to the level surface at the point 1, 2, 1. Does everyone understand this? I'm trying to do this as slow and as annotated as possible. We're all okay with this? Perfect. So that means the equation of the tangent plane would be 4 times x minus 1 plus 4 times y minus 2 minus 6 times z minus 1 equals to 0. So 4x plus 4y minus 6z. Now this is minus 4, minus 8, so minus 12. Minus 12 plus 6 is minus 6, minus 6. Move to the other side, it's 6. We can divide by 2 and say 2x plus 2y minus 3z is equal to 3. So this is the equation of the tangent. I don't know if they want you to simplify like this or they want you to leave it like this. That's up to the people who are going to grade your paper. But I'm giving you literally all the options. Is this okay? Okay, can we do some harder problems now? The highlight is, people always want to do harder problems, and I would like to do also a harder problem with you. Okay, so let's do a couple of harder problems. So here we go. So this is from 2020. No, 2020. And this would be number 6. There we go. This qualifies as a slightly harder problem. So let's do this. Again, I'm not giving you any more new theory right now. I'm focusing on some slightly harder problems. Let's see. Can you explain why you set the equation of the tangent plane equals to 0? Because that's how we find the equation of the tangent plane. And if the 4 was different, it would mean absolutely nothing. It would still get the exact same surface. As long as, by the way, as long as 1-to-1 satisfies this, as long as 1-to-1 happens to be on the surface. So how do you get that 4, by the way? If you didn't know that this was a 4, you would plug 1-to-1 into this, and that would give you the 4. Right? But in terms of calculation, it wouldn't change anything, right? T of 1-to-1 is equal to 4. That's how we get that 4, by the way. So good question, John, just to add a layer of, but it doesn't get into the calculation at all. The idea that it's 4 is because if I plug 1-to-1 into this, it would give me 4. And why is this equal to 0? Because that's how we find the equation of the tangent plane, Anonymous. If we go back to when we first met, this is how we find the equation of a plane. Right? If we have the normal ABC, and if we have a point x0, y0, z0, then this is how we find the equation of the plane. Any other questions? So are we ready for some slightly harder questions? Right. So first one is, A curve C is the intersection of these two surfaces. Find a parametric equation for the line tangent to C at this point. Now, this is definitely hard. So we want to find parametric equations of the line that is tangent to C. So basically, we want the direction of the tangent line, right? The direction of the tangent line to C. And C is what? C is the intersection of the two surfaces. Please, please, please pay attention. This is very confusing to some people because it uses some notions of linear algebra that you may have forgotten. Right. C is the intersection of both surfaces. So C is, let's go through this step by step. C, let's call this surface 1, and let's call this surface 2. Right, so this is, if you want, we can call this fxyz. So this is fxyz, and this is g of xyz. So this is level surface 1, this is level surface 2. So C is surface 1, actually let's not use level surface 1, intersecting level surface 2. So far, are we okay? So let's say this is the first level surface, this is the second level surface, and where they meet, C would be like the line right here. Do we see it graphically? C would be just this line right here. So this surface intersecting this surface, and that's C. That's the curve of intersection of both surfaces. Right, so C belongs to both surfaces. Yes? I'm going to assume yes. Now, the gradient of F is perpendicular to C. Of course, at the point 2, 1, 1. Or anywhere really, it doesn't matter at 2, 1, 1. Because why? C belongs to the level surface 1. So C is in level surface 1. And the gradient of F is perpendicular to level surface 1. Therefore, the gradient of F is perpendicular to C. The gradient of G, we called it G, is also perpendicular to C because the same explanation, and change surface 1 to surface 2. So the direction of C is perpendicular to two other vectors, right? So the tangent to C is perpendicular to the gradient of F, and this is the key word, perpendicular to the gradient of G. Of course, we're talking at the point 2, 1, 1 now. So at the point 2, 1, 1, let's assume the point is here. We have the gradient to this surface is perpendicular to it, and the gradient to the other surface is perpendicular to it. So we have a direction that is perpendicular to two other things. So the tangent to C is perpendicular to the gradient of F and perpendicular to the gradient of G. What's the direction perpendicular to two other vectors? What's a direction that's perpendicular to two other directions? This is the linear algebra part that I don't know if you remember. Here you go, Johnny. Good job. It's the cross product. So U cross V is a vector that is perpendicular to both, here is the keyword, both U and V. Therefore, here's the direction of the tangent. Since it is perpendicular to both the gradient of f and the gradient of g, is the gradient of f cross the gradient of g, of course, at the point 2, 1, 1. So we find the gradient of f, we find the gradient of g, we do the cross product, that gives us the direction of the tangent line. Cool? Let's go ahead and do it. What's the gradient of f? Derivative with respect to x, derivative with respect to y, derivative with respect to z. The gradient of g is 4, 3 minus 5. Of course, we're only interested in those at the point 2, 1, 1. So the gradient of f at the point 2, 1, 1, when x is 2, that's 4, 8 minus 10. The gradient of g at the point 2, 1, 1 is 4, 3 minus 5. And now we need to do the cross product. So what is the gradient of f cross the gradient of g? Do you remember your cross product? So we open up a new vector. We say, I put them on top of each other. I say plus, minus, plus. So for the first component, it's plus. Cancel this. Get the determinant of what's left, which is minus 40 plus 30 is minus 10. Then take minus, cancel this, take the determinant of what's left, minus 20 plus 40, that's 20, plus, cancel this, that would be 12, minus 32, that's minus 20. Of course, we don't actually need to take minus 10, minus 20, minus 20. So we can say the direction divided by minus 10. So the direction is 1, 2, 2. You don't actually need to get, like, if the direction of a line is this, then the direction of a line is this, then it's this, then it's this, then it's this, right? So the size of the vector doesn't really matter in terms of just direction. And the point is 2, 1, 1. Therefore, the tangent has parametric equations, direction t plus point. I will go over the cross product, Ryan, for you in general. I will do you one better. Here's the idea of cross product in general. So if the vector u is u1, u2, u3, and if the vector v is v1, v2, v3, how do we find u cross v? Right, so remember, we take plus, cancel this, do the determinant of what's left, which would be u2 v3 minus v2 u3, then minus do the determinant of what's left, which is U1 V3 minus V1 U3. Then plus, cancel this, do the determinant of what's left, U1 V2 minus V1 U2. And that is a vector that is perpendicular to both U and U and V. Sorry. The vectors U and V. Cool. Thank you for asking. Okay, so this was difficult, but not insanely difficult. All you had to do was remember that you had to use the cross product. The next one I show you will be quite something. So the next one I show you will be quite something, and that would be number 6 here. We're gonna go back to that part B because that part B is directional derivative, and I want to do directional derivative tomorrow. So this one, let's put some spices next to it. This one definitely qualifies as spicy, and it's from 2020. It came on other midterms. It's not just the only year that they gave this. So this came on other midterms. You will be able to check that out on other midterms also. Cool. So let's go through this example together. It is time to take a break. I don't know. I'm always at the second break. Shall we take? Shall we not take a break and continue and end early, or shall we take a super short break and come back? Shall we take a regular break? I don't know. I could go with all of the above options. If we don't take a break now, we can end a little bit earlier. People are saying different things. So far, the earlier break. There's so many anonymous attendees. Okay, so we're gonna do the sort of the halfway. Shall we take maybe just 5 minutes? There's you're saying everything all over the place. So maybe just 5 minutes so we can start attempting the problem, rest for a bit, and then end a little early. So the best of both worlds. Is this okay? So right now it is 7:58. Let us be back at, let's take 7 minutes at 8:05. It's a nice round number. Right, 7 minutes. So you can attempt this problem if you wish, or take a break and just, stretch your legs, and then come back and we will do this problem and maybe 1 or 2 more problems like this. And then we'll call it a session, and tomorrow we'll start with the rest of the topics. There's not a lot of topics left, but we're going to cover all of them super nicely. Okay, see you guys in just a bit. Hi again. So, here we are. Find 2 points on the surface at which the tangent plane to the surface would contain this line. So, very important. We want to find points on the surface where once we do the tangent line, it would contain this line right here. And this line is not necessarily on the surface, this line is somewhere. So look, we're going to start by saying, what does a point on the surface look like? So a point on the surface looks like is, let's just use is, A and then B, and then Z, C is this. So A squared plus B squared plus 5. So that's a point on the surface. Now, we are looking for A and B. So just as a note on the side, we are looking for A and B. So let's find the tangent plane at the surface. So how do you want to find the tangent plane? You want to find the tangent plane by making it a level surface, or you want to find the tangent plane by using fxy, whatever you want. So let's use fxy. So this would be fxy. How you find the equation of the tangent plane is entirely up to you. I'm going to use the linearization because it's simple. So z is equal to f sub x at ab times, sorry, I keep forgetting the first one. Z is f at ab plus f sub x at ab times x minus a plus f sub y at ab y minus b. Great. So f sub x is equal to 2x. So at the point AB, f sub x is going to be 2a. F sub y is 2y. At the point AB, f sub y is going to be equal to 2b. And of course, f of AB, we discovered that earlier, is a squared plus b squared plus 5. So z is equal to a squared plus b squared plus 5 plus 2a times x minus a plus 2b times y minus b. Now, what is this? This is the equation of the tangent plane. Are you with me so far? Now, what do we know about this tangent plane? This tangent plane contains x is equal to t, y is equal to t, and z is equal to 2t. And here's the keyword, and you know I reserve pink for the very important stuff. For all t. So whatever t you choose, this plane will contain x is equal to 2 to t, y is equal to t, and z is equal to 2t. This plane contains this line for any t. So if I were to replace this in here, so 2t is equal to a squared plus b squared plus 5 plus 2a times t minus a plus 2b times t minus b. This equation is true. This equation is true for any t. So it's not true for some t and true for not for, like, it's true regardless of what t is. Now let's sort it out a little bit. So this is 2t is equal to a squared plus b squared plus 5 plus 2at minus 2a squared plus 2bt minus 2b squared. So if I move this to this side and collect the t, that's going to give me 2a plus 2b minus 2 times t minus a squared minus b squared plus 5 equals to 0. Again, I'm going to write this again. This is true for all t, for any t. If this is true for any t, then what? This is the kicker. If this is equal to 0, regardless of what t is, then what? Then this must be 0, and this must be 0. This is 0 regardless of what t is. So 2a plus 2b minus 2 must be 0, and then minus a squared minus b squared plus 5 must equal to 0, because this equation must be true regardless of what t is. And if you reach this point, then the rest is just algebra. So this, you can say that a is equal to 1 minus b, because if you get 2a is equal to 2 minus 2b, then you divide by 2, then a is equal to 1 minus b. You replace that in here. So minus 1 minus b squared minus b squared plus 5 is equal to 0. So minus 1 plus 2b minus b squared minus b squared plus 5 is equal to 0. So that would mean moving everything to the other side. 2b squared minus 2b, this is minus 4 is equal to 0. So b squared minus b minus 2 equals to 0. So b minus 2, b plus 1 equals to 0. So either b is equal to 2 or b is equal to -1. And since a is equal to 1 minus b, a is equal to -1 or a is equal to 2. So this would give us 1 point. This would give us another point. So we could just, find them. The points, I remember, the points are this. These are the points. So this would give us the point a squared plus b squared plus 5. And this would give us the point a squared b squared minus 5. Good question. Do we get this? Okay, let's assume you got this. There was another nice question I wanted to look at. Tangent planes, there was here. See, this one is the exact same one. It was asked in 2017. It's the exact same question. Oh, here we go. That's a nice question. Here's another non-typical question. I think this is 2017, but I'm not 100% sure, so just check my question. So, find the equation of the tangent plane to the surface at this general point, and at what point does it intersect the z-axis? At what point does it intersect the z-axis? So I'll give you 30 seconds. The first part you should be able to do no problem. So this part should be no problem, the first one. The second part may be problem, we'll see. So I'll give you a second to look at this problem. So this is fxy. So f sub x is equal to minus 2x. F sub y is equal to minus 8y. At the point AB, f sub x is minus 2a. F sub y is equal to minus 8b. The equation of the tangent line of the tangent plane is z is equal to f at AB, and let's just do f at AB here since we're doing all the points here. F at AB is equal to 16 minus a squared minus 4b squared. So this is f at AB, 16 minus a squared minus 4b squared, plus f sub x, so minus 2a x minus a, minus 8b y minus b. There's no issues there. Everybody should be able to get this. Yes? We could have done it using a level surface, no problem. So we could have moved this here and created the level surface, whatever. I can show it using a gradient, no problem. So let me just do it here. So, or I can make the equation z plus x squared plus 4y squared equals to 16. So this is my txyz equals to a constant. So the gradient of t is equal to 2x 8y 1 at the point a, b, and whatever, 16 minus a squared minus 4b squared. The gradient of t will be 2a, 8b, and 1. So if you do that, and this is the point, right? This is the point. So the equation of the tangent plane is 2a x minus a plus 8b y minus b plus 1 z minus this, so minus 16 plus a squared plus 4b squared is equal to 0. And notice that if you isolate z, you'll get back the exact same equation. right? If you just simply move everything to the other side. Look here, if you just keep z here and move everything to the other side, you're going to get minus 2ax minus a minus 8by minus b, then plus 16 minus a squared minus 4b squared. Do you see how it's exactly this? It's just exactly that. So that's the other method. No problem. I wonder how many anonymous are there. It's funny. So, at what point do we intersect the z-axis? At what point do we intersect the z-axis? So what is the z-axis? The z-axis is when we have x is equal to 0, y is equal to 0, and z is equal to some t. So we're going to take this, and then we're going to intersect the plane this. Now we know how to take a line and intersect it with the plane. So t is equal to 16 minus a squared minus 4b squared minus 2a times 0 minus a minus 8b times 0 minus b. So t is equal to 16 minus a squared minus 4b squared plus 2a squared plus 8b squared. So t is equal to 16 plus a squared plus 4b squared. And then you take this and you sub it back here. So the plane intersecting the z-axis is equal to the point x is 0, y is 0, and t is equal to 16 plus a squared plus 4b squared. How are we doing? Questions, comments? Of course, there's nothing special about the z-axis. They could have asked us to intersect any line, and then we would have done the same thing. We would have solved for t, and then take t and plug it back into the equation of the line. So the z-axis is just a nice line, nothing more, nothing less. Questions? Okay, so now let me just, before moving on to a new topic, let's just examine where we are right now. So we did tangent planes. We did both methods. We did that question of the weird tangent plane, which brings us back to right here. So we can start the, I want to do chain rule because it's simpler than directional derivative. I'm going to do chain rule, and then we will leave the rest of the topics for tomorrow, because that's like a 2-minute, like a 5-minute thing. That's literally like I mean, 15, 20 minutes. That's it. And then this is just one formula, and then we have contour maps. So we don't have a lot of topics left for tomorrow. I want to do chain rule today, and then stick to the same topics we did today. Leave the rest of the topics for tomorrow. So chain rule. This is rather simple. There's nothing complicated. And they don't usually ask direct question on chain rule. They ask some like nice questions involving, you know, other topics. I'll show you. So what's the idea behind chain rule? Chain rule with multiple derivatives. So it looks like this. you have a function f that depends on variables, let's say x and y. Of course, this is an example, then not all chain rule is like this. This is an example. Then x is a function of s and t, and then y is a function of s and t. So f is a function of x and y, then x is a function of, let's say, s and t, and y is a function of s and t. You could have however many number of variables you want. So in this case, for example, how would you find the partial derivative of f with respect to x? Because f eventually will be a function of x, right? So, for example, f, of s, I meant. Of course, f is a function of x. So f is a function of x and y, but then x and y are themselves functions of s and t. So how do I find the partial derivative of f with respect to s, let's say? And the trick is very simple. You follow every path that takes you from f to s. Every path that takes you from f to s, and then you add them. So the derivative of f with respect to x times the derivative of x with respect to s. Then add the derivative of f with respect to y times the derivative of y with respect to s. You take every path that takes you from y, from f to s, and then you multiply them. So, for example, what would be the partial derivative of f with respect to t in this case? So now you're going to take every path that takes you from f to t, and you're going to add them. So the derivative of f with respect to x, the derivative of x with respect to t, the derivative of f with respect to y times the derivative of y with respect to t. Let me give you an example of this. Let's say we have f of xy is equal to x squared plus y squared. And let's say x is equal to r cosine theta and y equals to r sine theta, which you will learn about later in your course. These are called polar coordinates. So what would be del f del theta? What's the derivative of f with respect to theta? Again, f is a function of x and y. X is a function of r and theta, and y is a function of r and theta. Technically, there is no theta. If in this settings, there is no theta. So let's make it x squared plus y cubed. Don't worry about it. You're going to learn about all this later in the course. Just for now, just change it to a y cube so you get something meaningful. So we're going to take every path that takes me from f to theta. So the derivative of f with respect to x times the derivative of x with respect to theta. The derivative of f with respect to y times the derivative of y with respect to theta. So f with respect to x is 2x, x with respect to theta, that's minus r sine theta. F with respect to y is 3y squared, y with respect to theta is r cosine theta. Of course, I can substitute x by what it was if I wanted. I can change the x to r cos, and I can change the y to r sine. So I'm going to write it down. This would be 2r cos times minus r sine plus 3r sine all squared times r cosine. An example. Let me give you another example. And this is more common in 172. we would have a function f of x and y, maybe even of z. And x would be a function of t, y would be a function of t, and z would be a function of t. So they would all be functions of t. So now you can ask yourself, what is df dt, right? Notice how I'm using df dt. Df dt, because now f is a function of one variable. Just f is a function of just t. So every path that takes me from f to t, so del f del x, because with respect to x, f is a function of multiple variables. Then dx dt, because x is a function only of t. Del f del y, dy dt, and del f del z, dz dt. Would it not be easier to make minus r sine, minus r sine? I don't follow. You make this y. You don't want to. You want to get everything in terms of r and theta at the end, right? You don't want to keep the y's in. Eventually, you want to get it in terms of r theta. So let me give you an example of this. So this is an example, I think, from, hold on, I can get it from here. Linear chain rule. Isn't this chain rule? Yeah, chain rule. Here we go. So I'll show you how they would ask you a question, not specifically saying chain rule, but it applies chain rule. Suppose that the temperature in space varies from one point to the other according to the equation T is equal to Fxyz. We don't know what T is, and I don't think I can erase this. So we don't know what T is, but we know that it's just some function of x, y, and z. And at a time t, a mathematical fly is at this point. So the position of the fly is given to us by this, where x is a function of t, y is a function of t, and z is a function of t. So thus, at the position t equals to 2, the fly is at time t equals to 2, the fly is at this position by plugging t equals to 2 in here. No problem. Suppose that the gradient at this point is this. So what is this? This is the derivative of t with respect to x at the point 4, 3, 2 is -1. The derivative of t with respect to y at the point 4, 3, 2 is 4. And the derivative of t with respect to z at the point 4, 3, 2 is equal to 2. At what rate is the fly experiencing temperature change at t equals to 2? So what's the rate at which the temperature change? So we want what is dt dt. So this is the rate of change of the temperature with respect to time at t equals to 2. This is literally what we just did. So the temperature is a function of x, y, and z. X is a function of t, y is a function of t, z is a function of t, and we want to find dt dt. So can you get me that, please, theoretically, but then fill in the blanks. So what is dt dt? This is how I've seen them ask the chain rule. I haven't seen them ask chain rule other than this, to be honest. It's always been something like this. So this is the derivative of t with respect to x times the derivative of x with respect to t. The derivative of t with respect to y times dy dt. The derivative of t with respect to z times dz dt. And we can write this t sub x dx dt is 2. Dy dt is 1. I'm looking here and I'm finding them because x of t, I can write it here, x of t is 2t, y of t is t minus 1, z of t is t squared minus t. So plus t with respect to z times 2t minus 1. And at t equals to 2, we're going to get dt dt, the rate of change of temperature with respect to time. T sub x is minus 1. T sub y is 4. T sub z is 2. And when t is equal to 2, that's 2 times 2 minus 1. So that's 4, 3, 6, 7, 4 minus 1 is 3. 3 times 2 is 6. 6 plus 4 is 10. 10 minus 2 is 8. Sorry. And that's how we usually get asked questions about chain rule, disguised as some, bug flying or temperature or whatever. This is how they ask the idea. This is how they ask the question about chain rule. Any questions? So the next topic at hand would be directional derivative. So I'm not doing it today. As I said, I'm going to do it tomorrow. So tomorrow we begin our session with directional derivatives. Please, please, please email me any questions that you may have, any questions you'd like me to solve, anything in particular that's annoying you or stressing you, assignments, past tests, I don't know, problems done in class. The only thing, and I should say this, I should have said this in the introduction, the only thing that I do not do is people who send me their work so I can correct it. Like, can you check if I've done this correctly? Or can you check if, like, where is the mistake in my work? That I honestly do not do, because you can imagine I'm teaching all over the country. If every person sends me